Well, first of all, I want to thank the organizers for the opportunity to do the talk. Today I'm going to speak about stable distributions with a complex index alpha. Let me start with some history. A random vector xi is called stable if and only if, for every positive numbers b1 and b2, there exists a positive number b and a vector a such that b1 xi1 plus b2 xi2 is identically distributed to b xi plus a. Xi1 and xi2 are an independent copies of the vector xi. It's a well-known fact that these vectors depend on the two parameters. The first one is alpha, and the other is the measure lambda, or covariance matrix. Well, alpha is greater than 0, or less or equal than 2. When alpha strictly less than 2, then Levi measures equals the following, capital lambda tilde, and lambda is the finite measure on the unit sphere. When alpha equals 2, then the vector xi is Gaussian. Today I'm going to call these distributions alpha stable, meaning that it is stable distribution with some parameter alpha. Well, now let me talk about some generalizations of these random vectors. The first one was given by Ukrainian mathematician Gleb Nestorovich Sokovich in 1965. He said that vector xi is called stable if for every matrices m1, m2 from some set calligraphic M, there exists a matrix M from this set and the vector A such that m1 xi1 plus m2 xi2 is identically distributed to m xi plus A. The choice of set M is actually up to us. Well, for instance, if calligraphic M is simply a set of every positive number times the identity matrix, then this is the definition of alpha stable random vectors. The next definition, which is more common nowadays, was given by Michael Sharpe in 1969. He said that a vector xi is called operator stable if there exists a random vector x, a sequence of matrices Mn, and a sequence of vectors An, such that we have this convergence. So Mn times the sum of xk minus n weakly converges to the vector xi. It is quite easy to show that these definitions are equivalent. It follows from the fact that, actually they both prove that fact that in both situations we have, these distributions have an exponent, which means that the Levi process xi of t corresponding to this vector xi is actually identically distributed to t to the power e xi of 1 plus at for every t greater than 0. E is the square matrix, and at is just a vector. Well, for classical alpha stable distributions, the matrix E is simply 1 over alpha times the identity matrix. Yes, I wanted to say that if Mn is also a positive number times E, then this is the definition of classical alpha stable distributions, alpha stable vectors. Now let me announce the main problem of my talk. First, let me remind you about this theorem by Levi and Feldgame. If x a random vector, and for some sequences of positive numbers bn and vectors an, we have this convergence, 1 over bn times the sum of xk minus n, weakly converges to xi, then xi is an alpha stable vector with some alpha. When d equals 1, this theorem was proved by Levi, I guess in the beginning of the 30s. And when d greater than 1, it was proved by Feldgame, if I remember correctly, in 1937. I want to know what happened if x is a complex valued random variable and bn and an are the sequences of the complex numbers. Let me start by defining the alpha stable random variables. I want to consider alpha from this set, absolute value of alpha minus 1 strictly less than 1, On the complex plane, it is simply this disk, open disk. And I need these 4 parameters. A is the real part of the 1 over alpha, B is the imaginary part, rho equals 1 over A, and gamma equals B over A. Interesting thing that the pair rho and gamma is actually uniquely defined, the parameter alpha. And instead of using alpha, I'm going to consider the pair rho and gamma. And due to the lack of time, I won't show you all the theorems. However, it's interesting that the most theorems depends on the parameter rho and vary from the parameter rho, and gamma is any fixed real number. And also, I'm going to consider 3 different situations: rho from 0 to 1, rho equals 1, and rho from 1 to 2. Now I'm going to define the stable distributions. Let mu equals this measure, dx over x to the power 1 plus rho lambda d psi. Lambda is the finite measure on this interval, which is actually the finite measure on the unit sphere on the complex plane. Due to the time, I'm not going to comment on these definitions. I'll just say that nu is the Poisson random measure with the intensity mu. Z is simply a complex shift, and nu tilde is the centralized Poisson random measure, which is simply nu minus mu. I guess for those of you who knows how to construct classical alpha stable random vectors using stochastic integrals, you know why I used 3 different definitions and why this is really natural. Also, I want to know that when gamma equals 0, then it is simply 2-dimensional random alpha stable random vectors. Well, in this situation, rho stable random vectors. Now let's move to the main theorems. First, I will start with the limit theorems. With the definition. I'll say that x belongs to the domain of attraction of the alpha stable random variable if for some complex numbers bn and an, we have this convergence. So the theorem, let x be in the domain of attraction of the 2-dimensional stable vector with the index rho and the positive multiplier. Well, this simply means that 1 over bn, the sum of xk minus some an tilde, converges to, xi tilde. And bn is positive. It's actually important in the theorem. Then x times e to the power I gamma logarithm absolute value of x belongs to the domain of attraction of the alpha stable random variable with this parameter alpha. Again, alpha uniquely defines from the parameters rho and gamma. As I said previously, gamma is any fixed real number. And the normalizing multiplier is 1 over bn to the power 1 plus I gamma. Well, I'll just rewrite this theorem. Logarithm absolute value of xk minus some an converges to xi. Xi is alpha stable random variable. Now let's move to the complex stable distributions. Actually, on this slide is the answer of the question that I previously announced. We say that x, complex valued random variable, is a complex stable if its domain of attraction is not empty. Well, here you can see a more accurate definition. And the theorem, if x is a complex stable random variable, then it's either degenerative or alpha stable with some alpha, or Gaussian random variable. Actually, since degenerative law is 1 stable and Gaussian is 2 stable, then this theorem can be formulated as the following. X is a complex stable random variable if and only if it is alpha stable for some parameter alpha, where alpha belongs to this set on the complex plane. 1, 2. It is this open unit disk and, not unit, and this point 2.
What do you mean by the generative?
Just a constant. The probability that xi equals constant is 1. And the last theorem of this talk is the theorem about algebraic. Oh, sorry, I forgot to say that I wanted to know that this theorem formulates exactly in the Levi's theorem. So the answer is absolutely the same, which it was in the Levi's theorem. However, in the two-dimensional case, it should be different. For instance, the vector x, y, where x, y are independent, x, for instance, Cauchy, and y, normal random variable, then this vector should be operator stable. However, it's not alpha stable for any parameter alpha. Now we move to the algebraic stability. In the one-dimensional case, or in case of alpha stable random vectors, the definition was for every positive numbers, so on and so forth. And then we can show that there is a representation using stochastic integrals. However, in this situation, first of all, we defined random variables as stochastic integrals, and now I want to show the algebraic stability. So let's fix gamma, which is not 0. The case when gamma equals 0 is well known. It's just two-dimensional alpha stable random vectors. And capital gamma naught is the logarithmic spiral, which defines the following way: x to the power 1 plus I gamma, where x greater than 0. Yes, I can show it here, something like this, for some parameter gamma. And the theorem is the following: for every AB from this set, AB are complex numbers, there exists C and Q such that xi1 plus bxi2 is identically distributed to 6i plus Q. Then either there exists a parameter rho greater than 0 and less than 2 such that xi is an alpha stable random variable, or actually there is a formula of alpha, rho over 1 plus I gamma, or there exists a parameter sigma greater or equal than 0 such that xi is a complex valued Gaussian random variable with the covariance matrix sigma squared times the identity matrix. Well, I guess all I wanted to say is that this is actually a distribution of stability by Sokovich, where we choose our set M the following. Well, no, it's not a good one. I'll write it, I guess, here. M is the set of the following matrices: X, cosine gamma logarithm X minus sine, sine cosine, where X greater than 0. Well, that's all that I wanted to say. Thank you very much.
Thank you for a nice talk and for the perfect timing.
Yeah, I tried.
Questions or comments?
Yeah.
Yes, please.
Could you remain how branch alpha apply to your definition of F-stable random variable?
How? Well, to where we can find alpha here. What?
Can you choose the next slide?
Yeah, sure.
And we have this definition.
Mm-hmm.
And in this definition, we can see branches Bn and An. But where parameter F?
What parameter?
Как отсюда выцарапать?
Well, I said that alpha is uniquely defined, and actually there was a formula. Well, here, alpha equals rho over 1 plus I gamma.
А как она в определении участвует? Потому что там есть параметр Bn, есть An, а где альфа?
В этом определении?
Да.
Нигде.
Она здесь не нужна.
То есть она вообще не влияет.
Нет, она однозначно отсюда находится. Это не могут быть произвольные.
Oh, yes, I understand. There is something like a typo, I guess. Belongs to the domain of attraction, just a random variable psi. I thought you were talking about theorem. That's why. Well, yes, I understand. Actually, there can be any psi, any random variable psi. However, for not alpha stable random variables, the domain of attraction is just empty set. Нет, в определении не обязательно считать, что случайная величина альфа устойчива.
Is there any generalization for multidimensional complex case?
Yes, I guess so. I think that the easiest way is that, well, I have... No, I don't have this Levi measure here. Well, we just need to consider stochastic integrals as the following. Well, for instance, the easiest case, we just need to add the vector S, which is just a vector on the unit sphere in the multidimensional case. And I guess the theorem for algebraic stability will be true when the normalization is simply complex numbers on the logarithmic spiral.
Да, здесь как бы получить обобщение на многомерные устойчивые, это добавление сферы единичной. А всякие еще более хитрые, ну, это какие-то там вот следующие кватернионы надо пытаться использовать, чтобы явно какие-то микросуммации записывать.
Наверное, речь не о сферах, а о полидисках, об умножении на сферу. Ну, в смысле,
Ну, умножить.
Да,
в
вот...
смысле не многомерная комплексная сфера, а полнотория.
Нет, я имел в виду вот такой вот стохастический интеграл.
Да.
Умножить на S.
Нет, это все-таки другое.
More questions? So let us thank the speaker again.
Thank you very much for your attention.